Up until this point in the class, we've only looked at first-order differential equations, meaning differential equations that contain a first derivative as the highest derivative that shows up anywhere in the equation. Starting now, we're going to take a look at higher-order differential equations. So differential equations that can involve second derivatives, or even third derivatives, or fourth derivatives, basically anything higher than 1. In this section, we're going to take a look at some of kind of the big picture theory ideas before we actually jump into solving these types of differential equations. The theory is difficult. There's going to be some things that are a little bit abstract, and this whole section is going to kind of be a bear. So let me just warn you in advance that you might want to make sure that you're focused when you go through this, because again, I think this is probably one of, if not the most difficult sections of the entire semester from a conceptual standpoint. Okay, so let's start with the non-scary parts. Let's just kind of come up with some definitions, some basic working terminology. So we're going to start by looking at linear differential equations. That's going to be the biggest focus. So a linear nth order, meaning it's going to have an nth derivative showing up in it. Initial value problem. And this term, initial value problem, means that I'm specifying an initial condition along with it. Takes the form of the following. So I'll have some an of x times dny dxn. So here's my nth derivative term, and the coefficient for that term may be some function of x. Then we'll have the next term, a sub n minus 1 of x, so some other function of x times a derivative, where this derivative is one less than the nth derivative, right? So we're going down in derivatives, and we would then go to the next term that would be derivative 2 lower than the original, and we would keep going until we basically get down to, we'll eventually get down to like the a1 of x term that involves having a first derivative term plus an a0 of x times y itself, so no derivatives. And that can be equal to some function g of x. And it's going to require multiple different conditions. So here's the form of the differential equation, and it's going to require n conditions. So let's think about what this would look like. So far, we focused on first-order differential equations, and they only required a single initial condition in order to figure out what that unknown constant c is that shows up when we integrate, right? Every time we integrate, we'll introduce one constant of integration, and we will require one initial condition in order to solve for that particular value of c. But in an nth order differential equation, we're going to have to undo n derivatives, meaning we're going to have to integrate n times. And each one of those integrations will introduce a new constant of integration. And each one of those constants of integration will require a separate initial condition in order to solve for that value. So the conditions might look like the following. Maybe we'll have y at some value of x naught is equal to y naught. So this would be our normal initial condition. But we'll also need to specify what y prime looks like. And maybe we'll need to specify what y double prime looks like, and so on and so forth, all the way up to the n minus 1 derivative. And I guess this does not have to be y0. This should be some other value. And this should be some y n minus 1. And notice, because our index started at 0, so we have 0, 1, so on and so forth, we only go up to n minus 1. We don't need to go all the way to n. or we would actually have n plus 1 conditions because we also have the 0 included as one of the conditions. So these would be our n conditions. And for it to be an initial value problem, all of these conditions are specified at the same value of x naught. That's what makes them initial conditions. So each condition is specified at x0. So that's one thing you'll notice. They all are evaluated at x0. And the n conditions allow us to solve for the n constants of integration that show up when we solve this thing. That's why they're there. Okay. So initial value problems are really, really nice. And we're going to see a contrast in just a second. But basically what makes them an initial value problem is that the conditions are all specified at the same initial value of x, in this case x0. I want to talk about something called existence and uniqueness. And before we jump into this, let me just write this down. Of initial value problems, so of solutions. And this is again for initial value problems, which I'm going to abbreviate IVP. So an initial value problem. So big picture. So far we've solved a bunch of differential equations and we found an answer. How do we know that that answer is the only answer? And before we even start a problem, how do we know that it's going to have a solution? That's the idea that existence and uniqueness basically correspond to. We're trying to decide whether a solution will exist, and once we find that solution, whether it will be unique. And it seems kind of obvious because every encounter that we've had so far with a differential equation led to the existence of a unique solution, but that's not always going to be the case. One thing that's nice, though, is when it comes to initial value problems, existence and uniqueness is relatively straightforward. So this is kind of the big picture idea. In this section, we're going to start talking about what do solutions in general to these higher order differential equations look like? How do we know that the solution is even going to exist when we get started? And if we find a solution, how do we know that that's the only solution? How do we know that there aren't other solutions? And so these are all the questions that I want to ask. And we've kind of taken it for granted up until this point that the answers to those were going to be simple, but they're not. Luckily for initial value problems, there is a relatively straightforward theorem. And so I'm going to just write this one down. When it comes to initial value problems, these things aren't too bad. So I'm going to basically let all of those coefficients that we just had up in this definition, so all these an of x, an minus 1 of x, and so on. So let's let those things, let an of x, an minus 1 of x, etc., all the way down to the a1 of x and the a0 of x, all those coefficients. And let's let the g of x, which was, just to remind you, our right-hand side of our differential equation. Let all of those be continuous functions, at least on some interval that we're interested in. So let these be continuous, well-behaved normal functions on an interval, the interval that we're interested in solving the differential equation on some interval that we'll just call I generically. And let's just make sure that the an of x term can't be equal to 0, because if this term was equal to 0, and we go back up to the equation here, that would mean this term was 0, it would kill off this entire piece, and we wouldn't actually have an nth order differential equation. If this term was 0, this would be gone, and we'd really only have an n minus 1th order differential equation. So we need to make sure that leading term can't be 0. at least not on the interval that we care about. Okay, if x equals x0 is a point that's somewhere in the interval I that we care about, then basically a solution is going to exist and it's going to be unique. So a solution of the equation up here, maybe it would be easier if I reference this. So let's call this equation 1. A solution of equation 1 exists, and furthermore, or at least on that interval, let me make that clear, and is unique. So you can basically treat this as a theorem. I'm not going to go into the proof of this theorem. It's very, very actually kind of dense, and it's not really important for what we need. But the idea is, if you're dealing with a differential equation that looks like this one right here, and it has conditions like this, as long as these functions, these coefficients, are well behaved, at least on some interval that we care about, and same thing with this one over here, the right-hand side, as long as they're well-behaved functions, we're going to get a unique solution to this type of differential equation. But it's important to note that in this case, an initial value problem, all of the conditions are specified at this single point x0 that's somewhere on the interval I. So everything we've done up until now, every problem where we've had some condition, that condition has been what we think of as an initial condition. And I guess we've done some without any conditions, but every problem with a condition, I should say, that we've done so far has involved an initial condition. That's how we can think about it. And hence is an initial value problem. Notice that this equation up here is linear. So as long as we have a linear higher order differential equation where all the conditions are specified at the same point x0, or if it's dependent on time instead, that maybe it's the same value t0, the same time, we're going to get a solution. But so far, we're already kind of limiting ourselves. We're talking about only initial value problems and only ones that are linear. We haven't had any nonlinearities in these. And in general, we're really not going to take a look at nonlinear higher order differential equations. They're total beast, and it's basically kind of just like a guess and check method to solve them. There aren't good methods for solving those things. But coming down to here, every problem that we've done, including the nonlinear ones that were first order, has essentially been one of these types of initial value problems. And all the ones that are linear are going to be well behaved. But this theorem, again, only applies to this equation. So it's only applying to linear differential equations. When it comes to nonlinear differential equations, as we'll see, things get a lot trickier. So we'll talk about that later. So basically, we've talked about initial value problems. But there are also types of problems called boundary value problems. And the difference between an initial value problem and a boundary value problem is that in a boundary value problem, all the conditions aren't specified at the same value of x naught. They're specified at different boundaries, so to speak, if you think about it spatially, at different points in space in the problem, often on the boundary of the interval I that we care about. So boundary value problems, which we will sometimes abbreviate as BVPs, where the conditions are specified at multiple points. Okay. So what do I mean when I talk about a boundary value problem? Well, I could give you the exact same type of differential equation. Maybe let's make it a second order one. So we have some a2 of x times the second derivative of y with respect to x plus some a1 of x dy dx plus some a0 of x times y equals some g of x. So this is the same differential equation that we did up here. I've decided to only take it up to a second derivative, so n is equal to 2 in this case. So it's the same differential equation, but the conditions are going to be different. Instead of specifying them all at the same point x naught, the boundary conditions instead of initial conditions are going to look like this. The boundary values could take the form of one of the following. Maybe it would be that y at some point a is equal to y0, and y at some other point b is equal to y1. So maybe a is on the left-hand side of our interval that we care about, b is on the right-hand side of the interval that we care about, and we've specified the values at the left and right endpoints. But you don't have to specify it, so this is one possibility. So let me phrase it that way. Boundary value possibilities. So one possibility is they could look like this. Maybe we separate them with commas. A second possibility is instead of specifying the value at the endpoints, I could say I want to specify what the derivative looks like at each endpoint. Maybe I specify the value at one endpoint and the derivative at the other endpoint, or vice versa. So we can do combinations. You can specify the actual value at the endpoint. You could specify what the slope is at those endpoints. You could do one of each, so the value on the left and the slope on the right, or I could do the slope on the left and the value on the right. And I can even combine these into more complicated messes that look like the following. I could basically take some combination of the two. So maybe there's some, let me just write this out and then we'll talk about, make sure it's clear on what I'm talking about here. Okay, see a lot of Greek letters here. So what are these conditions? They look much, much worse than these ones up here. And they're basically a linear combination of specifying both what y, so the value on the left, and the slope on the left, some linear combination. So in this case, the alpha 1 and beta 1, these are just the Greek letters alpha and beta with subscripts of 1. Those are just two coefficients, just numbers. And I take some linear combination of the two and say it's equal to some other third value. In this case, this is the Greek letter gamma, the lowercase letter gamma. And so we're just taking a linear combination of both, specifying the position and the slope on the left and setting it equal to a constant. And then this over here is identical, but for the right endpoint B instead of the left endpoint A. So some linear combination where these alpha and betas are just coefficients, they're just constants. We've got the value of y itself, and then over here we've got y prime, so the position and the slope, and some linear combination of the position and the slope is equal to some constant. So basically we're mixing and matching combinations of the ones above and creating one big, ugly, extra nasty looking condition. All of these are considered boundary value problems with different, obviously, boundary value possibilities. All of these are different possibilities. The problem with boundary value problems, as opposed to initial value problems, is we no longer have a nice theorem like this. we can have this same setup. We can let an and an minus 1 down to a0 all be nice continuous functions along with the g of x. We can have all those things be nice. We can have our linear differential equation, and it's still possible to get one solution, infinite number of solutions, or no solutions, depending on what the boundary values are that are picked. So if we come back to existence and uniqueness of, again, that same differential equation of solutions. Let me get my wording to match, of solutions. But now we're talking about boundary value problems instead of initial value problems. The idea is that even with a linear ODE, like the one that we specified, like equation 1 up there, there can be one unique solution, no solutions, or infinite solutions, depending on the boundary values specified. Okay, so basically the idea of existence and uniqueness is straightforward for initial value problems. If you've got a linear differential equation and it's an initial value problem, you're going to have one unique solution. But when it comes to boundary value problems, even if you've got your linear differential equation, just like the one that we've specified up here, so again, referencing equation 1 here, the same one that we were doing up here. If I've got this differential equation, but instead of initial conditions, if I have boundary conditions, it's possible to have one solution, no solutions, or infinite number of solutions. So how is this even possible? Let's take a look. This will make this hopefully a lot more concrete. So let's consider a differential equation that looks like this. Y double prime plus 4, see if I can write my 4 a little more clearly, 4y equals 0. So this takes the form of the one that we, equation 1 that we talked about before. It's a second order differential equation. The leading coefficient is 1. The coefficient of the y prime term, clearly there is no y prime term, so its coefficient must be 0. The coefficient of the y term is just 4, and our g of x, the right-hand side, is just 0. Turns out that this has a solution that looks like the following. So if we think back in the first homework, I asked a question about this, and you hopefully can reach back in your mind and kind of, or if not, you can reason your way to it now. I'm looking for basically an equation or some function that when I take a combination of the function itself and its second derivative, in this case a combination where I take 4 of the original functions plus the second derivative, I take that combination and it gives me 0. What that means is that this piece must cancel out this piece, right? So if I'm adding in this term and getting 0, this piece over here must be the opposite of this piece. I could literally just algebraically move this term to the other side, and I'd say that y double prime is equal to negative 4y. The idea here is I'm looking for a function that when you take a second derivative turns into the opposite of whatever it was originally. In this case, maybe with some extra factor out, a factor of 4 in this case. And the idea is those are sines and cosines. When you take the derivative of sine, you get cosine. When you take the derivative of that cosine, it becomes negative sine, which is the negative of the original function sine that we started with. So the solution to this looks like the following. It's going to be equal to y equals c1 times cosine of, in this case, 2x plus c2 times the sine of 2x, because either one of these individually, if I plugged in a cosine into here when you take the second derivative. So if I plug in a cosine here, if we take the second derivative, I'm going to get a negative cosine out of it. And the fact that I have a 2 in here, I'll pick up an extra factor of 2 by basically by chain rule every time we take a derivative. So I'll pick up a factor of 2 when we take the first derivative, and then another factor of 2 when we take the second derivative to give me basically it'll produce a factor of 4 that can cancel with this factor of 4 here. So this is what the solution looks like. We'll talk about how to get to this solution more later on, but intuitively that's all I'm looking for, is what is a function that basically flips sign when you take the second derivative. And it's cosines and sines flip sign when we take a second derivative. But let's think about what the conditions could be. So this is sort of the general solution. What happens if we start trying to solve for these constants? And incidentally, how many constants are there? There's 1 and 2. 2 constants. Why do we wind up with 2 constants? Because this is a second order differential equation. Every time we integrate, which is going to be twice in this case, we'll introduce a constant of integration. And that's how we wind up with, in this case, 2 separate constants, because we have to integrate twice. So consider the following boundary values that we could use. So if the boundary conditions, also sometimes referred to as the boundary values, are the following. So what if I say that y of 0 is equal to 0 and y of maybe pi over 2 is equal to 0? And what if I come up with another set? So let me write a few different sets down, and we'll think about what each of these might look like. The next one, I'll say that y of 0 is 0, and maybe y of a different point, pi over 4, is equal to 1. And let's do one other set. Y of 0 equals 0, and let's say y of, let's go back to pi over 2 again, y of pi over 2 equals 1. So just looking at these all seem like totally reasonable, feasible, possible boundary conditions that we could use. We've got 2 conditions for each set, and those 2 conditions should presumably be enough to allow us to eliminate both of the constants. But is that actually the case? Well, I want to think about what this might look like. So what happens if we plug in y of 0 equals 0? So let's plug in this first condition. So if y of 0 equals 0, then our differential equation, get it all on the screen at once here, is this equation right here. We get that the y value is 0 whenever the x value is 0. So c1 cosine of 2 times 0 plus c2 times the sine of 2 times 0. Well, in this case, 2 times 0 is just going to be 0, so I'm looking at the cosine of 0 and the sine of 0. The cosine of 0 is 1, and the sine of 0 is 0. So my equation becomes 0 equals c1 plus c2 times 0. But this term is gone. So what does it tell me? It tells me that c1 has to be equal to 0. So basically, by plugging in this first condition over here, we've eliminated one of the 2 terms. In this case, it was enough to eliminate basically this first term, the cosine part. So we've eliminated the cosine portion. And so our solution at this point now, before we plug in our second condition, is simply that we have y equals c2 times the sine of 2x. Right, that's what we've got left, is just this part of the equation has survived. We already found out c1 is equal to 0, so this part of the equation is gone. This is all that remains. And now let's think about these other conditions. Let's graph this thing, because this will give us some insight. Can we graph a simple sine function? So here's x, here's the possible y values, and get my picture of the potential boundary conditions. We'll come back to this in a minute. But what does a sine function, excuse me, what does a sine function look like? Well, it goes through the origin and it goes up, and then it crosses at some point and then goes down and oscillates back and forth. So let me draw that, at least get it started, and say that here is one of our solutions. Let's just say that's enough. What is this point going to be? So I know that this point is 0, but what is the x coordinate where this thing comes back down to Earth? In this case, the equation is y equals c2 times the sine of 2x rather than the sine of x. So if it just was the sine of x, we know that this would hit at pi, and then it would hit again at 2 pi and complete one full period. But because it's sine of 2x, it's oscillating twice as quickly. So this point right here is going to be pi over 2. So that is the value right here. It's coming down and it's hitting 0 again at pi over 2. And we can check. We could plug in pi over 2 here. We'd have the sine of 2 times pi over 2. The 2 times the pi over 2, the 2's would cancel, and we just have the sine of pi. And sure enough, if you remember your unit circle, the sine of pi is always going to be 0. So here's the point that we're looking at. But we haven't touched on what C2 is. So far, we've kind of just presumed that if C2 was equal to 1, for example, then we would have hit a height of 1 right there. But if C2 was a bigger number, maybe it's possible that C2 is 2, and then our picture would look like this. It would go up a little bit higher before coming down, right? Our amplitude would be double what it previously was. So it would go up to an amplitude of a height of 2 instead. It could be negative, and it could come down here somewhere before continuing on. Right? If C2 is negative, then our sine function would just be flipped upside down. So in all of these cases, the sine function goes through the point x equals pi over 2 and an amplitude of 0, regardless of what the leading coefficient C2 is. So let's come back to our conditions and think about what's going on here. In this first condition, it specifies that y of 0 is 0 on the left, which we've already taken care of according to basically that's what eliminated the cosine term altogether. And the second condition here is just specifying that at the right-hand side of the interval we care about, at pi over 2, the height is 0 again. But there's lots of different curves. We've just drawn 3 different curves that satisfy both of these conditions depending on the value we pick for C2. Right? If C2 is just 1, we get this solid line right here. If C2 is 2, we get this double amplitude height one here that, again, still comes back down and goes through that same point. Or if I made C1 be equal to -1, that's the one that flips it upside down and would be a curve that looks like this. So specifying this condition here isn't enough to let me solve for C2. In fact, we could see what would happen if we plugged in this condition to try to solve for C2. We're not going to get anything out of this. So let's just say, hopefully it's clear visually, this is going to have an infinite number of solutions. And again, let's just check real quickly, what would that look like? Sort of as a side note, maybe we can do it over here. What happens if, so we're down, we've specified our first condition, and we're down to this equation. What happens if I try to plug in that y of pi over 2 equals 0? What algebra will that give us? So that's telling me that I get 0 for y whenever x is pi over 2. Well, when I multiply those together, that's just going to give me pi. And this thing leaves me with C2 times 0. I get 0 equals C2 times 0. So what does C2 need to be in order to make this statement true? It can be anything. Any value we want to pick for C2 will satisfy this. This second condition wasn't enough to actually uniquely solve for C2. So we didn't get one single solution. Instead, we have an infinite number of solutions because any value of C2 works. Okay, what about for the second one here? This one specifies, again, that y of 0 is 0. So we've already gone through the conclusion that that gives us just this sine function. It kills off the cosine portion. But this one says that y at pi over 4 is equal to 1. So now it's saying, here's a point. At pi over 4, I want the curve that goes through this point right here. The height is equal to 1. Well, how many of these sine functions that we've got go through exactly this point? How many of these sine curves go through that point? Only one. Only this solid line that I've drawn. So this is going to give us a unique solution. Right? Specifying this point wasn't helpful because all the curves go through this point. But specifying this point was helpful because there's only one curve that can go through this point. So in this case, we get one unique solution. And in this case, what we'll find is the value of C2 is going to be equal to 1. So we could check that. What would that look like? So again, here's the equation that we're trying to solve for C2 with the condition that y of pi over 4 is equal to 1. So that's what we're plugging in. So it's saying that 1 is equal to C2 times the sine of 2 times pi over 4. 2 times pi over 4, that's pi over 2. The sine of pi over 2, so it's going to give me, so that's just C2. The sine of pi over 2 is just 1. And so we get 1 on the left is equal to C2 times 1. And so what does C2 have to be? In this case, C2 is equal to the value 1 that we just found. So again, basically, I'm just plugging in 1 for the value of y, pi over 4 for the value of x, and then simplifying this and finding that it gives us C2 times this whole mess simplifies to a 1. And that's why I've got this C2 times 1. This whole piece became the 1. So our whole equation is 1 equals C2 times 1. 1 equals C2 times 1, which specifies that C2 has to be equal to 1. We get one unique solution. Last one. What happens if I say I'm looking for the sine curve, because again, that's what this one eliminates, the cosine part, so we've just got a sine curve. But I want the one that goes through y of pi over 2 equals 1. So that's telling me it needs to go through, when x is pi over 2, the y value needs to be 1. It needs to go through this point. How can I get a curve that goes through this point? Well, I can't, because I've got a 2 right here. If I wasn't enforcing that the period of this or the frequency of this had a factor of 2 in here, then yeah, we'd be able to find a way to make this work. But that's not how it's set up. The solution, the only thing that I do have control over is trying to figure out what C2 can be. It's impossible to find a C2 that will make it so that this function is not 0 when x is equal to pi over 2. It's impossible to make a sine curve of this shape where the frequency, again, is a factor of 2 in there. It has to go through this point. It's impossible to make it go through this point. So this has no solutions. And algebraically, what would happen in that case? So again, we're trying to solve the same differential equation down here. And we've gotten to the same answer, y equals C2 times the sine of 2x. And we're trying to find, basically, what is the value of C2 that will satisfy this? And so it's saying the y value will be 1 when the x value is pi over 2. But when the x value is pi over 2, right, that is pi, what is the sine of pi? It's 0. So this gives us the equation 1 equals C2 times 0. Can you find a C2 that will make this be true? No, because it's multiplied 0. This right-hand side is going to be 0 no matter what. It's impossible to make it be equal to 1. So there is no solution. You can't find a C2 that'll make that true. So here's sort of the algebraic interpretation of actually plugging in and trying to solve. These are the types of situations you'll encounter when you get infinite solutions, one unique solution, or no solutions. And geometrically, here's what's going on in the picture, right? Basically, the curve has to go through this point. If you specify that the curve has to go through this point, there's a lot of different curves that are going to go through that point. If you specify some different point in here, then you'll, for sure get a unique solution. And then if you try to specify a point where you know the curve has to go through the zero that's not at zero, you're not going to be able to find a solution. And that's this last case that we found here. So this is the idea. When I say that boundary value problems are a little bit trickier, it's because depending on the boundary conditions, we don't know how many solutions we're going to get, or if we're going to be able to find a solution at all. So just keep that in mind. Okay, so let's kind of come back, circle back now that this concept is hopefully starting to sink in a little bit, and think about how we are going to approach solving some of these equations, assuming that there is a solution to be found. So assuming we've got a boundary value problem or an initial value problem, depending on the case, how do we even try to begin solving these? So how do we begin trying to solve higher order ODEs? Okay, so again, let's stick to, if I can write here, stick to equations of the form of that one that we were looking at. So basically, it has to be a linear higher order differential equation with all the appropriate conditions on the values of the a's, those coefficients. We're going to classify these in a few different ways. One is basically if that function g of x, that's the right-hand side. So again, what equation am I referring to? Let me just give you a quick refresher, come all the way back up here, wherever I wrote it. This is the equation I'm talking about. We're going to stick to these for now. How do we approach solving one of these? Here's the g of x I'm talking about. If this g of x term over here on the right is 0, so if g of x equals 0, we call these equations homogeneous. And they'll have one approach. If g of x is not equal to 0, then we call the equations non-homogeneous. And they're going to require some extra work. So we'll start, when we start solving these in the upcoming videos, we'll start with these homogeneous problems, then we'll move on to non-homogeneous problems. If all the values of a, so the a(n) of x, if that's equal to some constant, and so is the a(n minus 1) of x, that's equal to some possibly different constant, and so on and so forth, all the way down to the a0 of x. If all those coefficients are constant, right? We said that they could be functions of x, but if we're assuming they're not and they're all just constants, then this type of problem is called a constant coefficient problem. Very creative naming. And those are going to be, again, relatively straightforward to solve. If all these things are not constants, so you get the idea. If any of these are non-constants, if they are instead functions of x, these are much harder. Non-constant coefficient problems are in general much harder. We'll only look at maybe 1 or 2 total problems of this form. There's a few sort of classical well-known ones that show up because they have applications in physics. We'll maybe take a look at a couple of those, but for the most part, we're going to be sticking to these constant coefficient problems because it turns out there are a ton of applications even just for these constant coefficient problems. So here's some the point of this is just to introduce a little bit of new terminology. The main thing we're going to be talking about is the difference between homogeneous and non-homogeneous problems. And they'll have sort of different approaches that we can talk about. And then constant coefficient versus non-constant coefficient problems. And we'll talk about the different ways that we approach problems like that as well. Okay, so let's start with these guys, now that we've kind of classified these. Let's start with homogeneous problems. So homogeneous equations. So basically, for example, let me just write a few out, and we can make sure that we've got the classification all correct. So here's one, 3y double prime plus 2y prime minus 5y equals 0. Maybe here's another one, x to the fourth times y, fourth derivative. When I do it in parentheses like this, the indication is that it's not being raised to that power, but instead that is an indication that we're taking a fourth derivative. So maybe it looks like that, plus an x squared times the y double prime term, minus 4y prime, whatever, plus 2y equals 0. And maybe here's another one, x to the fourth, again, y of 4 plus, whatever, x squared, y double prime minus 4y prime plus 2y minus 1 equals 0. How do we classify each one of these? This first one, you'll notice, is a constant coefficient. All the coefficients of all the y terms are constants, so this is constant. And there is no right-hand side. And we've got to be careful about just saying right-hand side because, obviously I could have taken this term and moved it over. But basically, what we do when we write this out, to get it in the form of that equation 1, all the terms on the left need to have y's or some derivative of y in them. And it's only terms on the right that would involve no y's. So things like constants or anything that's just a function of x. That's what we would put on the right here. So in this case, there is nothing on the right. The coefficients are constant. This is homogeneous. And it's constant coefficient. This is going to be a problem that we're going to encounter all the time. We'll be able to solve these no problem in just another couple of videos. This next one, you'll notice the coefficients are no longer constants, right? They're functions of x. But you'll also notice that, again, the right-hand side is 0. So this one is still homogeneous because basically there's no right-hand side. The right-hand side is 0, but it's not a constant coefficient. So it's a non-constant coefficient problem. This last one is probably the trickiest of all. Hopefully it's obvious. It is not a constant coefficient problem. It also has a 0 over here on the right-hand side. So at first glance, it looks like it could be homogeneous. But it's just, I've intentionally set it up to be tricky. By including this minus 1 on the left-hand side, if we go back to the original equation that we're supposed to be comparing this to, because again, we're really only solving equations of this form, the stuff on the left-hand side of the equal sign all involves y or its derivatives. So any term that was a constant must be something that we would normally wrap into the right-hand side. I've just written this one down here in such a way that that minus 1 showed up on the left. I could have rewritten this alternatively. So let me cross this out. I could have just rewritten this as equals of 1 over here. And that would make it more obvious that this one is neither homogeneous, so it's non-homogeneous. And it's also a non-constant coefficient. It's neither. Right? And it's, again, a little bit tricky. This one was homogeneous. There was no constant to worry about. everything that showed up on the left-hand side involved y or its derivatives. But this one had one term that did not involve y or its derivatives. It was a constant. And so by moving that over to the side where it belongs, we see that we do in fact have a g of x that's non-zero. So hopefully that makes this a little bit more clear. But basically, how do we solve these? Well, these are the problems that we're going to focus on first. So in general, to solve a non-homogeneous, if I can write this, non-homogeneous ODE, it's going to require us to solve the homogeneous version first. And then it'll require some more extra work. So what I'm suggesting is, if I had this same equation, but it had a 1 over here or an e to the x or any function that made it non-homogeneous, I would still start by solving this one, by pretending there was a 0 here and solving it that way. And then we would have to figure out what to do with the other part. So the question is why? Why do I need to solve the homogeneous one first before I start jumping into the non-homogeneous one? If we start with the non-homogeneous one, why can't we just start with the non-homogeneous one? Okay, so in what I'm about to write, I want you to basically assume that all those conditions I mentioned before, so all the coefficients that show up here, they're all continuous on a defined interval I, yada, yada, yada. So assume all of that is true. Assume the leading coefficient can't be 0. And when I say that, I mean it can't be 0 at any point in the whole interval that we're concerned with, right? So these x to the fourth, it's not normally 0, but at x equals 0, x to the fourth is 0, and this term would be gone, and this term would be gone, and we'd suddenly have only a first-order differential equation. So we'd need to be careful. It can't be 0 anywhere in the interval that we're interested in solving. I also want to introduce some notation. So things are about to get a little bit hairy so that we can talk about how do we piece solutions together. It'll make more sense once we start doing this, but I need you to understand the theory behind it. And to understand the theory, I want to introduce a little bit of notation. I just want to introduce the idea of something you've seen before, operators. You may have just never had them called operators. But operators are things that basically just transform one function into another. Right? So there's some very simple ones. Multiplication is an operator, right? I can take 2 times some function and it transforms it into a new function that's just twice what the old function was. You can add stuff, that's a transform. But so are other more complicated things. So for example, taking a derivative can be thought of as an operator, right? We transform one function into a new function by differentiation. And so I'm going to define that particular operator because we're talking about differential equations, derivatives show up, and I'm going to call that operator D. So D is going to be what we call the differential operator. And all it does is it takes a derivative. Why am I introducing this notation? Just because it's going to make things so much more compact and require so much less writing in just a few minutes. So all this thing does is it takes derivatives. One other thing I want to define while we're here, and I'll just call it again for the time being a capital L, this is going to be some generic operator that has to be a linear operator. And we'll define what a linear operator is in just a minute. But basically, this can be any operator that's linear, and we'll define linearity in just a minute. So I guess maybe now is a good time to do that. What is linearity when we're talking about operators? It's different than like linearity of a function. And so this is the very confusing part. Suddenly the word linear has different meanings. but it's related to the one that we just talked about. So it's related to the idea of us having a linear differential equation, right? It doesn't mean that it necessarily represents a line. It just means that there's no weird complicated versions of y times y prime or anything like that. So in the context of an operator, what is linearity? Linearity is basically a preservation of these two properties. So if you take a linear operator of some constant times some f of x, it has to be equal to c times L of f of x. So basically, for a linear operator, you can pull constants out. That's one property of a linear operator that has to be preserved. The second one is that when you're dealing with a linear operator and you have it applied to a sum of two different functions, so we're applying some linear operator to the sum of two different functions, that's the same as the sum of the linear operator applied to each of those two functions individually. Okay, so these are the two properties. These two properties are required. If something satisfies these two properties, it is linear. Okay, so let me come back to this notation and let's look at some examples of see kind of what this notation means. So what would it mean if I, using this notation, did d parenthesis of sine of x? What does that even mean? Well, the linear operator, the differential operator d being applied to sine of x means it's going to take the derivative of sine of x. So what's the derivative of sine of x? Cosine of x. So this is how the notation would work. D of some function will spit out the derivative of that function. What if I wanted to take the second derivative? So notation-wise, what we would write is d squared of sine of x. And this is, again, a notational thing. You could think of it as d of sine of x, right? So this first inner d will take the derivative of sine of x, and then the outer d will take the derivative of that. And the notation, so that we don't have to write d parentheses d parentheses d if we're taking higher and higher and higher derivatives, is we'll just do d raised to some power out here. So we'll have d squared is our second derivative operator. And all it would do is basically, it's the equivalent of doing d squared dx squared of sine of x, which would give us negative sine of x, right? It gives us the second derivative. And in general, d to the n will be the operator that does the nth derivative. So that's the idea. So what if I wanted to write out, so we can use this to write our ODEs a little bit more compactly. So again, let's do another example. Y double prime plus 2y prime minus y. How would I write that? Well, that's interchangeable with, so what is the first operator that's being applied to this term? Well, it's y, but it's the second derivative. So this must be d squared of y. And oftentimes, let me write it like that, d squared of y, plus the next thing that's being done is I'm doing 2 times the derivative of y, and then the last one is just minus y itself, so minus 1 times y. And because this y shows up in all of these terms, and based on the properties of differentiation, you can think about this as basically being the following. We could write this d squared plus 2d minus 1 of y. So this is kind of the idea that I'm trying to get at, is we can basically combine the individual operators that takes individually a second derivative here, multiplies by 2 and takes the derivative of y here, and then just does a -1 times y here, we can basically take all of those out and combine them into one big operator. And the reason for that is because differentiation is a linear operator. What you can see is essentially all we're doing is doing something like this. I just did it in reverse. I said, if we write our equation like this, we could think of it as a bunch of different kind of operators being applied separately to these different pieces. And we could kind of factor them out and treat it as one big operator just being applied to y. So it's kind of related to this idea. Not exactly, but this is kind of the idea here. So this is a linear operator. This right here is a linear operator. And even if there were x's in here, it would still be a linear operator because, so this is a linear operator. Hence, if I set this equal to 0 or some constant, we'd have a linear ODE. And it's because we can satisfy these two properties up here. So basically, what we're saying is that in general, we could think of our operator as looking like this. an of x dn plus an minus 1 of x dn minus 1 plus dot 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 plus a1 of x d plus a0 of x. So this operator, which you can think of as the operator for our original equation, way back up here, the whole left-hand side. So we multiply by an of x and then take the nth derivative of y. And then we multiply by an minus 1 of x and take the n minus 1th derivative, and so on and so forth. You could think about this one as being one big operator being applied to y. That's the point of this notation, is it allows us to write the original equation as just simply going to be this new big ugly mess, L of y. So L of y equals g of x is a compact way to write equation 1. So part of the point of introducing this notation is because you may see it again in future classes. The second part, the reason that this notation exists to begin with, is because it's so much more compact than writing out a giant equation every time. We can define our linear operator one time and then just write simply L of y. And L of y would refer to basically plug a y into all of these different parts, and we're back to having the left-hand side of equation 1. And so in this case, it's just L of y equals g of x is our equation 1. And again, it's because it's linear, we can treat basically doing L of y and break it up into all these separate pieces. You can pull constants out. You can do all of that good stuff. But it's going to allow us to basically show that if we can verify that these two features, these two properties are satisfied, then our operator is linear. And I could show it for this particular giant operator that we just did, but essentially the gist of it is we know differentiation is a linear operator because differentiation has this property. So for us, okay, let me try to summarize this here because I feel like I'm starting to ramble. L of y is linear. And it's because if you look at the way that we just defined this particular L of y, it's really made up of a bunch of d's. And so instead of showing you individually for this whole giant thing, let's just think about why is the differentiation operator linear. So, which is itself linear. So basically what I'm saying is if you take the derivative of a constant times some function, what can you do with the constant when you take a derivative? Well, you can always pull the constant out, right? That's one property of differentiation. Similarly, what happens if you take the derivative of the sum of two functions, right? Like a polynomial. Instead of taking the derivative of the whole thing at once, we can take the derivative of each term in the polynomial separately, like an x squared term plus an x term, and find that the result is simply going to be the sum of those individual derivatives. So what it's saying is, in this case, the derivative of the sum is the sum of the derivatives. That's all we're finding out here. So the derivative operator itself is linear. If we were to extend this, we could write the exact same thing of what we've got here. It would just be a much longer thing to write out, which is why I'm avoiding writing it, because it'll take up like half the screen. But basically, each one of these pieces here is a linear operator. And so we've just constructed a big linear operator of all these individual linear operators, which is the derivatives. So basically, if there was a constant that showed up in y, you could pull it out of the whole thing. If we wanted to apply this operator to the sum of two separate functions, we could absolutely break it up and write it separately as the sum of these two separate pieces. This is going to be important because we're going to use that property in just a few minutes. So, so where am I going with this? Why do we care? Okay, number one, compactness. I already mentioned this. Equation 1 is now that we've defined this particular L that we're going to use, is now simply L of y equals g of x. Easy. Don't have to write that out. Second reason, and this is going to be a more important reason, it makes a property that we're about to talk about called superposition. Very clear and easy to understand. Okay, so what is superposition? What are we talking about? Basically, the idea is that if you can find a solution to our differential equation, and then you can find another solution to the differential equation, then the sum of those two will also be a solution. So basically, superposition says that if you can find multiple solutions to a linear ODE, then the sum, and even more than the sum, furthermore, any linear combination, so it doesn't just have to be the sum of the functions themselves, but the sum of any constants times those functions, which again, we'll come back to this. But it will also be a solution. Okay, so let's see kind of what I'm talking about. Hopefully this will make more sense. So let's let y1, y2, up to yk all be solutions. So the nth order homogeneous ODE given by, and it's also linear, the linear nth order homogeneous ODE given by L of y equals 0. Okay, so L of y again refers back up to equation 1. The left-hand side, all we've done is set the g of x to be equal to 0. So it's homogeneous. Then it turns out y equals some constant times y1 plus some other constant times y2 plus ... some other constant times yk is also going to be a solution. Where the c's are constants. Okay. The proof of this is actually pretty straightforward based on the definitions, but this is going to be the idea. So let's just let k be equal to 2, so there's only 2 solutions. Just to make life easier, but this idea extends up to more. Then what it tells me is that basically y1 and y2 are both solutions of L of y equals 0. What does it mean if they are solutions? Well, this means that L of y1 will be equal to 0 and L of y2 must be equal to 0. That's what it means for them to be solutions. So now let's consider the combination. So we'll call it some other y. That is the combination c1 times y1 plus c2 times y2. Remember, the c's are constants. These y's could be functions of x. So just keep that in mind. So let's see what it looks like if I now try to plug in this as a possible solution of our differential equation. So then in this case, we'd have L of y is equal to L of c1 y1 plus c2 y2. But we know that by the properties of this linear operator, I can split that up as separately L of c1 y1 plus L of c2 y2. And furthermore, right, so this was one property of a linear operator that says if you have the linear operator applied to the sum of two functions, you can break that up as the linear operator of the two functions individually. And the second property of a linear operator was that we could pull constants out. So I can rewrite this as c1 times the L of y1 plus c2 times L of y2. But what is L of y1 and what is L of y2? So this one's going to be c1 times L of y1, but we already know that because y1 individually is a solution of the differential equation, that this term will be equal to 0. This is what it means for it to solve this differential equation. So it's going to be c1 times 0 plus c2 times L of y2, but we also already know that L of y2 has to be equal to 0 for y2 to be a solution of the differential equation. So that is also going to be 0. And what do we get? 0. So therefore, if these two pieces individually are solutions, then this combination of them, when I plug that in, will also be a solution because it will give us L of y equals 0, which is what it means to solve the differential equation. So basically, the whole point of this is if I can find a bunch of individual pieces that solve the differential equation, then I can create linear combinations of them using the idea of superposition to come up with a more general solution. We can use multiple solutions of an ODE, of a linear ODE, I should say, right? Because all has to be this linear operator of a linear ODE to create a more general solution to the ODE via superposition. And what is superposition? Again, superposition just means exactly like we did here, we take a linear combination, right? So constant times the first one, different constant times the second one, in general, all the way up to, if we have k different solutions that we found, any linear combination will also be a solution. Okay, the only requirement is we only want to include linearly independent solutions. Okay, whoa. So what on earth is a linearly independent solution? So let's see if we can think about what that means. Basically, let's define it here. If I've got a bunch of functions, so let's say we've got this list of functions. Functions f1 of x, f2 of x, dot, 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 up to fn of x. So we've got a big long list of functions. These functions are linearly independent if the only solution to the following, to C1 F1 plus C2 F2 plus dot 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 plus Cn Fn equals 0. So that's the equation. Is that C1 equals C2 equals dot 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 all the way up to Cn, and they're all equal to 0. So basically what it's saying is these functions are linearly independent if and only if the only solution to this equation is that every single coefficient has to be 0. So essentially what it's saying is, if you think about this, is there's no way for one function to cancel out another function. So essentially, no function should be possible to write as a linear combination of the others. So maybe this will be more clear. If I had a couple of functions, if I had x squared, and the function x squared plus x. These are not linearly independent, so this is my f1, f2, and my f3. These are not linearly independent. I'll just abbreviate it Li, because I could take f1 plus f2 minus f3 and get 0, where these coefficients are basically a 1, and a -1. Instead of having all these coefficients, they're not all zeros, right? If I add this and this, I've got x plus x squared, and then I subtract this, which is x squared plus x, it'll be enough to cancel both of these terms, and we'll wind up with 0. But the coefficients themselves are not all zeros. So these functions are not linearly independent. But if I just took any two of them instead of all three of them, then they would be linearly independent. But in this case, we've got three possible ones. And so those three equations are not linearly independent of one another. I don't know why I'm erasing that. It's a good example. So let me leave that there. Okay. So, how do we know if our functions that we find are going to be linearly independent? And again, why do we care? So let's go back to big picture. We're talking about solving differential equations. We've basically said, assuming that our differential equations are linear, as long as we can find some solutions, then any combination of those solutions will also be a more general solution. We're going to use these to construct the most general possible solutions. We have some idea about the way that conditions play a role. It's possible to maybe have no solutions, one solution, or infinite solutions if we're dealing with boundary conditions, as opposed to initial conditions, where in general, initial conditions, if we've got a linear differential equation, it's going to have one unique solution, whereas with boundary values, not going to be the case. So those are kind of the big picture ideas so far. Okay, so we're getting there, I promise. Just bear with me. This is going to go a little bit longer. I'll try to wrap it up as quickly as possible. Okay, so assume that we found a set of solutions. To our ODE. So hypothetically, we found a big set of solutions. How do we know if they're linearly independent or not? Well, we're not going to always just be able to, by observation, kind of pick out that, oh no, I can find a combination of these functions that cancels each other out and gives me 0 without all the individual coefficients all being 0 of each of them. So that's not going to be possible. But one way we can determine this is with a tool from linear algebra. We'll compute something called the Wronskian. And again, this shows up in a number of different things. Comes up in some advanced kind of vector calculus classes. For now, you don't need to worry about it too much. Let me just give you kind of the definition, and then we'll see how it works. So suppose the functions f1, f2, and so on and so forth up to fn assume these all possess at least n-1 derivatives, meaning they're functions that you can take the derivative of at least n-1 times. And if that derivative eventually winds up being 0, that's totally fine. The derivatives just have to exist. If that's the case, then the determinant, which looks like the following, so we're going to use this notation, w of f1, f2, ... fn. So notationally, this is just going to be ugly. This notation is just meant to define the following. And hopefully you've seen these. If you've taken Calc 3, you will have seen these. If you've done the cross product at any point in any class, you will have seen determinants. But it looks like this. f1, f2, ... fn. It's basically a big matrix, but we're interested in the determinant of that matrix. Then below this, we'll put all the derivatives, the first derivative. So f1 prime, f2 prime, ... to fn prime. And then below that, we'll go the second derivatives, right? F double prime of 1, f double prime of 2, f double prime of n. And then so on and so forth until we get all the way down to the n-1 derivatives. So f of n minus 1th derivative of the first one, f n minus 1th derivative of the second one, f n minus 1 derivative of this nth term. Okay, this is called the Wronskian. If you have no idea, if this looks super intimidating to you, don't worry about it too much. We'll do an example of one of these in a little bit, and for like just a 2x2 matrix, which is basically what pretty much the only thing we're going to encounter in this class, this is going to be pretty straightforward. So it looks scary. If you're familiar with matrices, this might not be as scary, and if you're unfamiliar with matrices, this is probably terrifying looking. But I promise we will do an example. I'll come back to this later. Turns out the functions that we just defined, those f's, f1, f2, dot, 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 up to fn, are linearly independent if the Wronskian of those functions is not equal to 0 for all x on the interval of interest. Okay. So again, for now, don't worry about this. We'll do some examples down the line. I will compute some Wronskians for you. You can see how it's done for a 2x2 matrix. It's not that scary, but it basically has to do, there's a procedural way that you basically multiply a bunch of these functions together and then add the results up in a bunch of ways and see, and eventually you just get a scalar out of it, a scalar quantity. So, okay, so we'll come back to that. But this brings us to the big important idea. We ultimately want the most general possible solution. To an ODE. Again, like the one that we've been doing, this big L of y equals 0, or L of y equals, for now, let's just stick with L of y equals 0. To do that, we need to basically find all the possible solutions that we can then combine to create this most general possible solution. And we call all of those solutions the fundamental set. So fundamental set of solutions. Okay, so again, before we delve into this, again, try to give a quick recap of what we've talked about so far, because I know how dense this is. So the first thing we did was kind of differentiate between initial value problems and boundary value problems, and just say that basically, big picture, boundary value problems are trickier than initial value problems. Second thing we talked about, when we're dealing with these big differential equations, as long as they're linear, we've got some hope. And it's possible to find solutions to these big linear differential equations. And if I can find more than one of those solutions, then any combination of the solutions will also be a solution. Right? So if I can find one function that solves the differential equation, and I can find another function that solves the differential equation, and those two functions turn out to be what we're calling linearly independent, I can combine them together to create an even more general solution. If I can find every single one of those possible solutions, then we can create the full general solution. The fundamental set of solutions is that set that I'm looking for of all possible individual things that we could plug in to create the most general possible solution. Okay, and here's how it works. Any set y1, y2, up to yn of n linearly independent, right? So basically, you can't write one in terms of the others, or as a linear combination of the others. So any combination of n linearly independent solutions of the linear homogeneous nth order ODE given by our L of y equals 0 is said to be a fundamental set of solutions. Okay, on the interval of interest at least. Okay, so what is this telling us? It's telling us how many solutions we need to look for. If we've got an nth order differential equation, we should expect how many? N linearly independent solutions. If we can find n linearly independent solutions, then we've got everything we need to create our full most general solution. So this means a second order differential equation, we should be able to find 2 linearly independent solutions that can be combined to form the most general solution. If it's a third order differential equation, we need to find 3 solutions. If it's a fourth order differential equation, we need to find 4 individual solutions that are linearly independent to create our full set. And it turns out, as long as our equation is linear, this will always exist. So basically, it'll always exist for equations of this form, our linear homogeneous differential equations of any order. Okay, we'll use this set we'll use the fundamental set to create what we're going to call the general solution. And again, for now, we're just talking about homogeneous, reinforce that, homogeneous differential equations. So we're still talking about L of y equals 0. Okay, so this is what we're trying to form, the general solution. Basically, if you have a bunch of your y's that you found, if y1, y2, ... up to yn are a fundamental set of solutions, then the general solution, and I should say of solutions to L of y equals 0, then the general solution is just the linear combination of all of them. So the most general solution will be C1y1, plus C2y2 plus ... plus Cn yn. Linear combination of all of those solutions, where the C's are arbitrary constants. Okay. So let's do an example. In this example, I will also compute the Wronskian so we can verify that our solutions that we found are linearly independent and therefore form our fundamental set, and then we'll use them to construct the general solution. Okay, so let's look at an example of how this kind of all fits together. Let's do one similar to the one that we started with, a little bit different. Let's consider y double prime minus 4y equals 0. So this is, again, our linear homogeneous differential equation. In this case, it's a second order differential equation. So we need 2 linearly independent solutions to form our fundamental set. What are some solutions that will work? Let me just tell you 2 right off the bat, and in the next video, we'll talk about how we find these. But for the time being, let me just give you the solutions. So this has solutions. y1 is equal to e to the 2x, and y2 is equal to e to the negative 2x. And you can verify by plugging in. What's the second derivative? Excuse me. What's the second derivative of e to the 2x? Well, when I take the first derivative, I'll get e to the 2x with a factor of 2 pulled out. And when I take the derivative of that, I'll get e to the 2x with another factor of 2 pulled out for a total of 4e to the 2x. And we'd plug that in here. We'd get 4e to the 2x minus 4e to the 2x, which is 0. And do the same thing with this one. When I take the second derivative of this, I'll get a negative 2 and then another negative 2. So I'll again have 4e to the negative 2x. And I'll plug that in here. 4e to the negative 2x minus 4e to the negative 2x. And they'll cancel each other out and we'll get 0. So these are both things you can plug into this and verify you get like a 0 equals 0 situation. So you can plug them in and verify that both of these are solutions. And they're solutions on the whole real line, right? Any x you want, these are solutions. What does the Wronskian look like? So let's verify that these two solutions are what I call linearly independent, or what we've been calling linearly independent. So for the Wronskian, it's the determinant of a matrix. And in this case, it's going to be a 2 by 2 matrix because there's only two things that go into it. So the first thing we need to put in are the functions themselves, e to the 2x, e to the negative 2x. If you reversed the order and did the negative one here and the positive one over here, that would be absolutely fine. That is still the Wronskian. It would give you the same result, so it doesn't matter. So the order of these two doesn't matter. Below them go each of their derivatives. So what's the derivative of e to the 2x? That's 2e to the 2x. What's the derivative of e to the negative 2x? That's negative 2e to the negative 2x. When we're computing a determinant, whoa, boy, we've written a lot on this one. Okay, so how do we compute this determinant? And again, if you've done a cross product before, it's the same idea. You'll be familiar with this notation. I'm going to do the product of these two, and then from that I'm going to subtract the product of these two. So what we're going to get when we compute the determinant is going to be e to the 2x times negative 2e to the negative 2x. Right? So this was our first pair, this one times this one. And from that I'm going to subtract this one times this one. And for us, this is all you need to know. The formula gets a little bit more complicated when you get to like a 3 by 3. But I will certainly on exams and things of that nature, I'm never going to give you more than a 2 by 2 system. We'll stick to second order systems. So you don't need to worry about those for the other cases. So the other product I need is the product of these two. So that's going to be e to the negative 2x times 2e to the 2x. And so what do I get from this? Well, when we do this multiplication, I've got an e to the positive 2x times an e to the negative 2x. We add exponents, and we'll just get e to the 0, which is 1, times a negative 2. So I've got a negative 2 from this first term. And from that, I'm going to subtract, so let me just do it in the square brackets so it's clear where each piece came from. So this whole thing here in these first square brackets became a negative 2. From that, we're subtracting whatever we get from here. So same thing, e to the negative 2x, e to the positive 2x, add the exponents, they'll become 0. We have e to the 0, which is 1, times a 2, so this whole piece is just a 2. So I've got negative 2 minus 2 for a total of negative 4, which is not equal to 0, which implies that they are linearly independent. So that was our check. If you go back to the Wronskian thing, we said as long as the Wronskian is not equal to 0 for all the x on the interval, and for us, right, we just got a constant, right? The x dependency totally fell out of the problem altogether. So we got a constant, so it wasn't equal to 0 anywhere. And so they're linearly independent solutions. This means, so y1 equals e to the 2x, and y2, which is e to the negative 2x, are a fundamental set. I know they're a fundamental set because it's a second order differential equation and we needed two equations that were linearly independent. We found they were linearly independent. There's two of them, so they're a fundamental set. And the general solution is y equals c1 e to the 2x plus c2 e to the negative 2x. That is the general solution. And you could go back and, if you wanted to, verify. So take the second derivative of this expression, plug it back into the original differential equation, and you would indeed see that it satisfies the original differential equation. Okay, so the last question, and then I promise we'll be done with this hugely conceptual, mind-numbingly long video. What if the ODE isn't homogeneous? So far, what we just did, coming up with this general solution, this was for a homogeneous equation. What if it's not homogeneous? In this case, the solution needs yet another piece. That we're going to call the particular solution. So it's going to be another thing that will solve a different part of the equation. So think about how it's going to be set up. What we'll get in this case is our solution will look like this. It will look like y is equal to y homogeneous plus y particular. So I'm going to call this the homogeneous solution. I'm doing the subscript of h to stand for the word homogeneous. So this is the homogeneous solution, and it's the piece that we just found, basically, right? It's the solution in our book. If just confusingly enough, the book uses y with a c for the subscript, but I think h makes more sense. So just keep in mind, if you're reading the book, they'll use the letter c, but I use the letter h. Basically, L of YH is equal to 0. It satisfies that equation. We'll have a second solution. This is the one that we're going to call the particular solution. And luckily the book does use y sub p for the particular solution. And it solves the equation L of y particular equals g of x, where this is the non-homogeneous part. So we're going to have this part of the solution, the YH, solves this part. The YP will solve this equation. And the general solution is going to be the sum of these two pieces. So this piece solves the homogeneous equation. This is a particular solution. It solves the particular equation that involves having the non-homogeneous term on the right-hand side. We'll spend a bunch of time focusing on how to find these particular solutions later, but let me just show you why this would work. So let's imagine that we plug this in to the equation. So this whole thing will solve the linear but non-homogeneous equation that looks like this. So my goal is to show you that this general equation solves this equation, even though this piece individually solved the homogeneous part and this piece individually solved this equation. So let's think about what's going on. So I'll do L of y. But because it's linear, so let's just make it totally clear, L of YH plus YP. But because it's a linear operator, when you take the operator of the sum, that can be split into the two separate pieces. what did we just say this has to be equal to? So if YH is the part that solves the homogeneous equation, then it means it satisfies this equation. So this first piece must be equal to a 0. And then the second piece, we just said solves the particular solution. So it solves this particular equation. So L of YP must be equal to G of X. And what do we get this whole thing to be equal to? G of X. And so if I compare this to what it's equal to, we have that L of Y equals G of X. So what I'm suggesting is there's going to be multiple parts that go into the equation. Sure, we can find something that solves this equation, but it's not going to be the most general solution we could find unless we also include the part that solves the homogeneous solution, because when we put it all together, the part that solves the homogeneous solution won't contribute anything additional that would skew what the G of X looks like. The particular solution will take care of the G of X. The homogeneous solution is just enough to give us the most general possible solution of something that still solves the whole equation. So this is basically it. This is the idea of superposition, essentially. And the idea of superposition, incidentally, superposition works on the particular solution as well. So what do I mean by that? So particular solution 2, I should say. Basically what I'm suggesting is if we have an equation that looks like this. So we've got our big left-hand side, our big nth order linear differential equation, and it's equal to, maybe there's a bunch of different pieces that make up the non-homogeneous part. Well, then it turns out we can find maybe one function, y1, that solves this equation. We can find a second one, y2, that solves this equation. So basically I'm suggesting maybe we can find a function that solves, if we ignored this part, we could find a y1 that would just solve this equation. If we ignore this part, we could find a different y2 that solves just this equation. And so on and so forth. Basically find one solution that satisfies, gives us each piece of the non-homogeneous part. And then we can basically put it together. So I could call this, I guess I should maybe do these as, because they're all particular solutions, I should sneak some p's in there. Then basically the most general form of this particular solution could be the superposition of all of these individual pieces. So the yp1 plus the yp2 plus ypn. Okay. So superposition works basically whenever you're dealing with a linear operator. It works for the homogeneous parts, and I'm telling you now it also works for the non-homogeneous parts. And we can use these ideas to basically construct our full solutions, and we should have some sense of what the solution should look like ahead of time. The form of the homogeneous solution will be constructed of n separate pieces, where n is the order of the equation, right? So a second order equation, we should look for 2 separate pieces to make up the homogeneous part of the solution. If it's a third order, we should be looking for 3 pieces, and so on. And then similarly, for the particular solution, there will be different things. And if the particular solution is made up of multiple different pieces, because the non-homogeneous part has a bunch of different pieces, we can find a bunch of different individual particular solutions that satisfy each of those individual pieces, and the general version of the particular solution will be the sum, the superposition of all of those other pieces kind of together. So it's kind of like the idea of superposition applied to this as well. Okay, so again, I know this video is going on like 2 hours now, but total big pictures. Basically, 3 main ideas from this video that I hope you walk away with. The first one is, for our higher order differential equations, we have initial value problems and boundary value problems. Initial value problems are easier if you've got a linear differential equation that's higher order, you're going to have a solution to an initial value problem. A unique solution will exist. Whereas if you have boundary value problems, no solution is guaranteed. It's possible to have one unique solution. It's possible to have no solutions. It's possible to have an infinite number of solutions. So initial value problems are easy. Boundary value problems a little bit trickier, just because there's more possibilities in terms of the outcomes. So that's big idea number one. Big idea number two, if we're trying to find the solution to a homogeneous equation, the solution to the homogeneous equation will be made up of n linearly independent solutions that form what we call the fundamental set. If we have an nth order differential equation, again, we're looking for n separate pieces that are going to make up the homogeneous solution. And the last thing is if we have a non-homogeneous equation, so there is a g of x term on the right-hand side, then the most general solution will be made up of the sum of both the homogeneous solution and a particular solution that satisfies basically the right-hand side that we're looking for. And so we will use this idea to construct our general solutions. We'll always have to solve the homogeneous problem to get some pieces, and we'll also have to solve the particular solution to get the full general solution of a non-homogeneous problem. So that's our third idea. Hopefully this makes some sense. I know it was incredibly long. If you've stuck through it all the way till now, congratulations. We'll be moving to much more reasonable problems in the next video where we actually start solving some of these things and just putting some of these big picture ideas to use, which will hopefully make them a little more concrete.